Okay, so we'll reference this sheet in just a minute. Let's at least go to our notes though. Section, where are we at? We're gonna kind of tie in 4.2. So we're gonna go right to 4.3. And I'll tell you why. So we're gonna go right to section 4.3, part 1. And we're going to talk about what's called, I think we've said it a couple times. Well, we talked about integrals, but we're going to be specifically evaluating definite integrals. Okay, so first of all, what is that? Before we learn it, we got to know what it is, right? Okay, so we are finding integrals. What does integrals find us? The area under the curve. So we're now going to start algebraically finding the exact area under the curve. All right, and we'll write that in just a minute. And a definite integral tells us exactly where we're starting and stopping. It has endpoints, or remember the fancy word for those endpoints are limits. Right? So a definite integral, should we write it again? All right, let's write it again. A definite integral. Okay. The definite part is saying that it has limits. I guess we didn't have to write it again. Tomorrow, we're going to be talking about an indefinite integral, where there are no endpoints. And what does that mean? Or there are no limits. Remember, limits are just the endpoints. A start and stop. Okay. And then the integral finds us the area under the curve. Let's see. All right, so the official way to write this, well, let's back up just a minute. Let's cover 4.2 in a nutshell, all right? Before we had all the rules for derivatives, what's the first thing we used to find a derivative that caused us to pull our hair out? We used limits, right? Okay, so what is the official way to find the area under the curve? Limits, all right? So 4.2 says the limit as n approaches. Now, n is your number of rectangles. How many rectangles do you want? Remember, the more rectangles you have, the better your answer. So we want the number of rectangles to head to infinity. So as your number of rectangles heads to infinity, and then we actually write it like this, and that's why we're not going to do a lot today. The summation, have we ever seen that before? It means to add. It's a sum notation. And does that make sense that we want to add up all these rectangles? All right, the sum of, and it's I equals 1 to infinity as well. Or I'm sorry, it's actually to n, but where n is infinity, but we're going to write it as n. And then, does this at least make sense? The function x sub I times delta x. What is going on there? This is my width, and this is my height. This is my width, and oh, this should say I. Did I say that? I don't know. That should say I, because I want different heights, right? I want when my height is 1, I want when my height is 2, I want when my height is 3. Okay. So in years past, I actually did this, but it does get a little dicey, and we are actually a day short, so we're not actually going to do the limit. If you're sad, I'm sorry. I looked online, most people said we should do it, but what do we do after we spend a day crying on limits? We learn shortcuts. Okay, and this one is extra dicey because it does use this summation, and that's something that we really haven't worked on. So we have to first learn all about the summation, and then we still have to go do limits. So there's a little bit more to it. But in general, you can do the area under the curve using limits. Now, after they did enough of these, what did they start realizing? So here's the shortcut. So instead of doing limits, maybe we can sneak it in. The shortcut. Now, this is what you want to write down. The shortcut. Okay. This is, first of all, we can say the notation for integral is like a long S. All right, and then we go from A to B. Now that's stuff we're used to, right? This is the start. This is the stop. We call this the lower limit and the upper limit. And a lot of times I just call them endpoints, but lower limit, right there, lower limit, and then this is the upper limit. Oh, what else? And then we do f of x. That's our height, right? And then instead of delta x, we're going to use dx. So here's my width, and here's my height. Just like up here, I forgot to label it. This is our width. Even though it's with limits and it seems a little intimidating, can we at least see that this is our width and this is our height? Okay. Same thing here with the shortcut. This is our width and this is our height. But we actually don't end up doing too much with the width. It's actually just the height that can determine the area under the curve. So here it is, our shortcut is equals capital F using the B number minus capital F using the A value. Now, what is capital F? Does anyone remember? If our function started with F, capital F was the antiderivative. Yep, so both of these you find, so this is antiderivative. Antiderivative. So you find the antiderivative of this guy. And then you plug B into it, you plug A into it, and you subtract those two answers. And instead of doing limits, you can take the shortcut. You're going to find the antiderivative of this guy, plug B into that antiderivative, get a number, plug A into that, get a number, and subtract those two numbers. Oh, let's see. What else? Oh, let's do a little of this. If you want to watch, I could probably, I probably could type this up for tomorrow. Properties of integrals. Properties of integrals. So if I got the integral, it may be good to write it a few times, kind of get used to doing that long S from A to B. If I have f of x plus g of x, so now remember, and then I have my dx after it. Remember this kind of represents terms. So if you are adding, it is okay to do each part separate. So it is okay to do the integral of just the first function and then add it to the integral of just the second function. Okay, so if you're adding, it is okay to split it up if you need to. And maybe we could shorten it and just do this. If you are subtracting, same thing. It is okay to split it up. But that's it. You have to be careful for multiplication. We don't have any rules, kind of like derivatives. Remember, we had some other rules for multiplication. So we'll talk about that the next couple days. There isn't great ones for multiplication. There isn't one consistent one for multiplication. So we're going to learn one today, and then we'll learn some more, I think, towards the end of the week. So multiplication is a little bit harder. There is one other one we can write, or 3 others. If you have, and this one we do use, if you have a number, just a constant, some number that maybe you could factor out of the entire function, you don't even have to worry about that. You can actually do the integral, leave a little bit of space. You can actually do the integral on that reduced function and then take your answer times that constant. So I would say it's so funny. It's like, okay, we have a number, let's get rid of that number. When do we get rid of a number in math, right? But we get rid of the number, do the integral on all our variables, and then later we can bring that constant back in. Okay? We can do the constant after we've done all the hard stuff, which is kind of nice, just one less thing to look at. Pull it out, get rid of it, put it off to the side. I guess this one's kind of weird, but let's look at this one. If we have the integral from a to b of f of x dx, this comes up, I think, more in Calc 2. If for some reason you want to split it, so we're going to do an integral from a and just to c of f of x dx, we can add to that an integral. Does anyone know where we would start? Do you see here, instead of going from, let's say, 1 to 5, okay, 1 to 5, I'm going to go 1 to 3, and then I'm going to go 3 to 5. Does that make sense? So then I'm going to go C to B. Let's draw a little picture too of f of x dx. If you have to break it in parts for some reason, you can do that. So this, let's draw it. I don't know. We could do this curve, and we're going from A to B. And we're finding the area under that curve from A to B. But if for some reason, and this is more Calc 2 stuff where it gets harder, if for some reason it's easier to find just this area and then this area, does it make sense? Then I would add them together. So I would just go from A to C, and then I would find the area under the curve from C to B, and then I could still add them together. This one we might use too a little bit. Remember, now I know it's hard because you guys are still doing stuff, but let's, for this last one, let's take a look at the shortcut. I know we barely used it. Do we still need it up there? Oh. Okay, so the shortcut is we plug in B, we plug in A, and then we subtract. Okay. So if, let's say my answer is 5 minus 2, I get 3, right? What would happen though if for some reason I did 2 minus 5? I'm pretty close, right? Because I get, instead of 3, I get negative 3. Right? All right, so let's take a look at this last one. This one says if, oh, let's do it. Can we even see this picture? Should I backtrack? Were we okay on that picture? All right. All right, let's write the last one. We want to get to examples. What's our last one? Okay, so our last one is if we got the integral from A to B of f of x dx. Okay. If I want it equal, now this is very important. If I want it equal, if I for some reason want to switch these, and if I put B down here and A here, I can do that, but I'm going to get the opposite, right? We just kind of said, like, on that other example. If I did 5 minus 2, I'd get 3. So here, if I would do 2 and 5, I would get negative 3. So to make them equal, you just have to put a negative out there. Because for an example, this would give me 3. This situation here would give me negative 3. To make it equal, I just tag on that negative, and then I'm back to 3. So if for some reason you need to switch those, then you just tag the negative. All right. All that. Let's see. One other thing, and then we're good. Okay. So don't forget that it finds us, the integral finds us the area under the curve from A to B. Area under the curve. Now, the last thing, and then we'll get to examples. What happens if we go below the x-axis? So let them go, and here's my B. Actually, this graph could go on. My B is where I stop, okay? And let's say, you know, my A could be here. A lot of times A is 0, it doesn't have to be, but the stuff above the x-axis is positive area. Positive area. But the stuff below the x-axis is negative area. So whatever's here, this would be negative area. So there's always that little bit, you know, your area is 7, but it could have been 10 above and 3 below. That's the only kind of downside about this, but sometimes it plays out. And you can actually then end up with an area of 0. How do you end up with an area of 0? The amount above and the amount of below were the same. This could be 10 and this could be negative 10. So then you actually end up with an overall area of 0. So that's kind of the only bad side. Or if you have a negative area, that's okay. Don't let that panic. You know, I think there might be one on the homework. There's one in our notes where we have a negative area. That just means at least more of it was below the x-axis. Okay, so that's maybe something a little bit different, but that's how it works. All right, so let's try some. Remember, be careful when the directions are short. These directions are short. Ready? Find the integral. Evaluate the integral. I think I took this from the homework though, so it should say find the integral. Is this even what we... Okay, first one, we are going from 1 to 2. So not a very big width at all, from 1 to 2. And it is a polynomial 4x to the third minus 3x squared plus 2x and then dx. And really, we should really have parentheses around this because this is really the width times the height. We end up for our shortcut, we really just focus on the height, but keep in mind this notation is still important. It's the width times the height. Okay, so now what was that shortcut? Maybe we should have wrote that last. Remember, our shortcut is antiderivative plugging in B, antiderivative plugging in A, and subtract. So the first thing, what are we going to find every time? We have to find antiderivative. Okay, so what is that? Add 1, divide by the new. Add 1, divide by the new. So we're going to add 1 takes us to x to the 4th, and then divide by the new. So those two should match. Okay? Depending how much you want to write, add 1. So that gives us x to the 3rd, and then divide by the new. So these two are the ones matching. There's a 1 already there, add 1. So that gives us x squared, and then divide by the new. Now this one turned out really nice. They won't all be like that, but First one should, right? The first one better. Okay, why do I say that turned out? So these all match nicely because 4 over 4 gives us 1. So we have x to the 4th minus x to the 3rd plus x squared. Now, we've already kind of started the process. So we've actually done most of the process. We found the antiderivative. So we don't want to use this notation anymore. So we go over here and we just kind of put a line and we write, we still have to go from 1 to 2. So we want to acknowledge that we've started the process. We're kind of like halfway through. So we don't use this symbol anymore. We go to the end and we write it like that. Sometimes some books will even put a little thing like that, but most of the time it's easier just to do a straight line. Okay, and then we plug in 2. We have to do, now this is our capital F, so we have to plug in a 2, 2 to the 4th, minus 2 to the 3rd, plus 2 squared. And then a minus and a bracket. And now what do we plug in? We plug in a 1. Make sure you do the B first. It always messes me up. This is A, this is B, but you plug in the B first. And then we plug in 1 to the 4th minus 1 to the 3rd plus 1 squared. So this is my f of B, this is my f of A, and then subtract the 2. So make sure that there's parentheses. You could even put parentheses around both. You need to do B, you need to do A, and then subtract. All right, so overall, I got this to be 12. 16 minus 8 plus 4. And then minus, well, this would be 1 minus 1 plus 1. And again, you would not have to write this, whatever works for you, however much you need to type in your calculator. Okay? If you want to type this whole thing into your calculator, you can, but you have to have parentheses around this. These must be there. So this is 1, so 11. Okay, what's that number? Whatever this graph looks like from 1 to 2. Oh, let's see, can you see? Okay, you can still see that. Whatever this graph looks like from 1 to 2, I should have done it on my calculator, but whatever that graph looks like from 1 to 2, the area under the curve from 1 to 2 is exactly 11 units squared. Remember, the only thing we don't put units squared because eventually that could actually mean distance. It can actually mean volume. But for right now, for literally what we did, it is 11 units squared under that area from 1 to 2. And this curve, whatever it is, and we could graph it in a minute, but that's the 4x to the 3rd minus 3x squared plus 2x. Under this curve from 1 to 2, that area is 11. All right, now it can't be that easy, right? It is, it's just that these can get harder. Okay, so let's take a look at another one. So we're going to go from 0 to 3. And it is 3x plus 1 times 5x squared minus 2, and then times dx. So this whole thing is my height, and this is my width. So this together, those two together are my height. That's my kind of like my f of x. My f of x is really this whole thing. And then, so that's my height, and then that's my width. Okay, now, what operation are we doing? Multiplication. What operation do we have no rule for? Multiplication. So what are we going to do here? We need to FOIL. Okay, yeah, that's the first thing we do with multiplication. We'll learn some other stuff later, but it's still honestly the easiest. Where maybe here, like if you were doing derivative, eventually you might want to say, oh, I could do the product rule. But for integrals, by far the easiest way is to FOIL. All right, so let's go from 0 to 3. All right, so this is going to be 15 x to the third. Add those exponents. Minus 6x. Inside gives us 5x squared, and then last negative 2. And then technically times our dx. And you could rearrange it if you like. There are no like terms, so we could just go add it. And then same thing, it's not pretty because notice when I add 1, I get a 4. And so I'm just going to have to deal with that. Our author kind of likes these crazy ones. So x to the 4th, and then it's going to be 15 over 4. There is a 1 there, so add 1. Okay, this one's nice. Add 1 takes us to 2. And then divide by the new. So those two match. Back to crazy, right? Add 1 takes us to x to the third, divide by the new. And then this one technically remembers x to the 0. So when I add 1 and then divide by the new. Add 1, divide by the new. Because we're taking the antiderivative. Since we started the process, we're not going to use that symbol anymore. We're just going to put a line. We still have to go, though, from 0 to 3. All right, we can clean it up a little if we want. This is going to stay 15/4. This at least will go to 3. This guy will stay. And then this can go to negative 2x. Go 0. So it'll probably help to have some type of calculator because it does get a little crazy. This number, I don't even know. This numerator is actually in the thousands, just the numerator. So sometimes that can mess with the calculator. But 15/4, and then you got to do 3 to the 4th minus. We do get lucky here. Let's talk about where we get lucky. 3 and then 3 squared. That's doable. 5/3 times 3 to the third minus 2 times 3. Maybe I'll even do it in red. Minus, and then don't forget your bracket. What do we plug in the next time around? 0. Yeah, so now we plug in 0. So it's 15/4, 0 to the 4th, minus 3 times 0 squared, 5/3, 0 cubed. I'm running out of room, but what happens when we multiply something by 0? We get 0, right? 0 times, doesn't matter, 0 to the 4th times 15/4 is still 0. So if you kind of want to just go through and write down 0, we got minus, I'm running out of room here, minus 2 times 0. But this bracket, because there is no constant, this whole thing, what does this whole thing turn out to be? That turns out to be 0. Yeah, can you see that? Now, this one, did anyone type it in? Oh, that's interesting. Yeah, this does cancel. So if you have a decimal, that's okay. Question.
I got plus 5/3 up there, but I'm not sure. This is minus and plus. So I got plus 5/3
For this?
up to 3.
Oh, okay. Hang on. Oh yeah, this should be. I don't know why. Yeah, this should be maybe because I copied it from here. This should definitely be plus. Yes. Sorry. Yes. Good call. Yep. And actually, it should actually be plus in here, but because of the 0, it doesn't matter. But yeah, this sign should just follow for sure. Yes. Sorry about that. Good call. All right. So I got 1,263 with that plus over 4. If you got 315.75, that should be the same. The only problem, if the decimal ends, WebAssembly should take it. If it's like in the thirds, then you need to change it to a fraction. Because as soon as you round, that it's not considered exact. On the test, if you give it like that, that's okay. Okay. Oh, Another thing you could do if you like, I don't know why, I'm always used to writing it out like this, but the other way you could do it, like if you want to do f of 3, so go to your, you know, this guy and just plug in a 3 and then do f of 0 and then just subtract those two. You know, that's okay, especially with a calculator. If you can kind of just do this with a calculator, maybe just put an answer for each one, something like that, that would be okay. That way it doesn't get too lengthy. Otherwise, if you just write it out, that's fine too. That's the only way I could think about shortening it. But I don't know, you'd still maybe be writing out the whole thing, write one on one level, one on the other, and then subtract those two as opposed to kind of always running out of room. All right, let's try another one. Let's do integral from 1 to 4. It's a fraction. 4 plus 6u over the square root of u, and then du. We're going to be working with u's a lot, so it's maybe in a good habit to see some u's come up. Okay, this one, we're dividing. We've got a rule for division. So we want to split each one up. So we're just going to rewrite it. 4 over the square root of u plus 6u over the square root of u. And then maybe we could have done it right away. The square root of u, we're going to write as u to the 1/2. So from 1 to 4, 4, and then u to the 1/2, and then 6u to the 1st over u to the 1/2. Right now, we just got to get it organized. So as soon as you see multiplication, you're going to FOIL. Division, you're going to split it up. All right, so the first one, what's the best way to write the first one? 4 and then u to the -1/2. Now, how do we put these u's together? When you're dividing, you subtract exponents. So 1 minus 1/2, that gives us a positive 1/2. And again, it's kind of weird. We need to write it for different situations, but we really don't do much with this. The shortcut comes from all the height. Maybe too, because this is all the same, right? It's always the same. This is standing for the width, which is always the same. All right, notice I use this symbol because I have not done anything with the antiderivative. This is all just rearranging. This is the same thing as this. So you just got to take your time to rearrange. Now we actually want to do the antiderivative. Add 1, divide by the new. Now just take your time with these fractions. Add 1 takes us to positive 1/2. Okay. Now I can either divide by a fraction or multiply by the reciprocal. So 4 divided by 1/2 is the same thing as 4 times the reciprocal, which is really just 2. Let's do this next one. So adding 1 here actually takes us to 1.5 or 3/2. And then 6 divided by 3/2 is the same as 6 times, maybe I'll do 6 over 1, 2/3. So 6 divided by 3/2, the same thing as 6 times 2/3. If you want to write it as, if you don't want to write this divide and multiply by the reciprocal right away, go for it. If you like to write it, so make sure it matches and you visually see that you flip it, then that's okay too. Right? We could write this as 4 over 1 and then times 2 over 1. Okay, so now I've done the antiderivative, so now I'm going to do my line 1 and 4. Okay, and this actually turns out okay, right? Because this turns out to be 8 u to the 1/2. Remember, if you want to write that back now as the square root of u, you can. And then this one, this turns out to be what, 12 divided by 3? So that gives us 4. This one's maybe a little bit harder. 3 to u to the 3/2. We could write this as taking the square root, that 2 is the square root, and then cubing your answer. We're going to take that bottom as a 2. So we're going to take the square root and then cube the answer. Okay, so now let's plug in the 4. So I've got 8 square root of 4. That's not too bad. And then I've got 4 times, I'm going to do the square root of 4 and then cube that answer. And then minus, and do not forget your bracket, 8 square root of 1 plus 4. I'm going to do the square root of 1 and then cube that portion. All right, so this square root of 4 is 2. 2 times 8, 16. Square root of 4 is 2. 2 cubed is 8. 8 times 4, 32. And this one's even easier because the square root of 1 is 1. So 1 times 8 is 8. Make sure I have my parentheses there, my brackets. And this one here, the square root of 1 is 1. Cubed is still 1. And then take it times a 4. Okay, so we got 16 plus 32 minus, and then this turns out to be 12. Turns out nice. That, oh yeah, can we see that? 36. If you have a calculator and you just did 4 to the caret 3/2, fine, more than fine. Right? Just good reminder what it means, but yeah, you can definitely, calculators now I think do 3/2. I think you could even put in 1.5 and you'll be fine as an exponent. What about, all right, and what, oh, let's back up. What does that 36 mean? What's that 36 mean? Which we can't even see. How about there? That's the area under this curve, whatever this graph looks like, from 1 to 4. The area under that curve from 1 to 4 is 36. All right, how about, let's go from 4 to 9. The square root, and inside the square root is a fraction, 6 divided by x dx. All right, this was maybe a little bit shorter. Let's split it up though. So you want to write this as the square root of 6. So that's just a number, maybe not one we're not used to working with, but we're going to have to. And then we've got the square root of x. You can split those up like that. This I'll probably just leave, square root of 6, but the x I like exponents with the x letter or variable. So x to the 1/2. And now where do I want to put that? I want to put it on the top in the numerator. So I've got this crazy number. This number can now be the coefficient. The square root of 6 and then x to the -1/2. Let's pause like that. Some of this is just rewriting. Okay, so we had to split this up into 2. Bring that x to the top, and now we literally have a coefficient and then an x. All right, so now add 1, divide by the new. So now we're there. So take your time with splitting it up. Add 1 takes us to +1/2. So that's kind of nice. Divide by 1/2 or multiply by the reciprocal. What's the reciprocal? Divide by 1/2, which is just multiplying by 2. Now I'm going from 4 to 9. So instead of dividing by 1/2, I add 1. So that gives me 1/2. Dividing by 1/2, same thing as multiplying by 2. All right, so now I got 2 square root of 6, and then the square, remember 1/2 means square root, so square root of 9, minus, and then I do it all over again, 2 square root of 6, and then I plug in a 4. All right, but the square root of 9 is 3, so what can I multiply here? I can multiply the 2 and the 3, and this is 6 root 6. Same thing here. Square root of 4 is 2, and I can multiply the 2's. So I've got 4 root 6. And because those are both root 6's, I can go ahead and subtract the coefficients. And so the area under the curve, the exact area is 2 root 6. So that one's kind of nice. It's small, simple, but it kind of covers a lot. And you get, it's kind of nice because you don't even get like an answer of 7 or 10, but you're getting an exact answer there. Without maybe, well, yeah, let's look at this. Integral from 0 to 1, so not a very big width, total even. X, and then parenthesis, the 4th root of x plus the square root of x dx. So x times the 4th root of x plus the square root of x, and then you got your width of dx. So same thing, we are multiplying, right? So what did we say? We got nothing for multiplication, so we want to distribute. We're actually going to kind of do the multiplication. Let's change these though, because when I multiply, what do we do with the exponents? We want to add them. So let's get exponents on that. X to the 1/4. And then this guy is x to the 1/2. We cannot add them because they're different radicals. One's a 4th and one's a 2. You cannot add those. But we can multiply. When we multiply, we add exponents. So this has a 1. So we're going to do, this is still, we can still use the integral symbol because we haven't done anything with the antiderivative. When we multiply, we add exponents. 1 and a 4th is 1 and a 4th, or we usually write it as improper, which is 5/4. This is kind of crazy. And then we multiply here. When we multiply, we add. 1 1/2 is 1 and 1 plus a half is 1 1/2, or 3/2. So now we got crazy fractions, and we still haven't done the antiderivative. It's kind of weird because we added 1, but that wasn't the antiderivative. Why did we add 1? Because we were multiplying the x's. Okay, so don't let that confuse you. Now we still go at it. So now we're going to add 1. 5/4 plus 1 takes us to 9/4. Divide by 9/4. This is maybe where we could save a little bit of time because there's no coefficient. Dividing by 9/4 is the same as multiplying by 4/9. Right. Add 1. 3/2 plus 1 takes us to 5/2. And then it's dividing by 5/2 or multiplying by 2/5. All right. Now, now we can do 0 to 1. Plug in a 1. So we got 4/9, 1 to the 9/4, plus, now be careful. This is actually kind of a good one. A lot of times when there's only 2 x's, people will put a 1 in here and a 0 in here. Make sure you do a 1 through the whole thing, and then go back and do a 0 through the whole thing. Okay? It's like if there's 3 x's, we remember, but for some reason, if there's 2 x's, then we put 1 in each. You got to do the whole entire function. So 2/5, 1 to the 5/2, and then we go back through minus, and then we do it with the 0. Now we get kind of lucky because what is 1 to any power? That's still going to be 1. So 1 times 4/9 is 4/9. 1 to 5/2 power, still 1. So 1 times 2/5 gives us 2/5. And we even get more lucky because what is 0 to 9/4 times 4/9? All of that is 0. So minus 0. And then same thing here, all of this is 0. So we don't even worry about that. So 4/9, oh, can we see? 4/9 plus 2/5. You do have to get a common denominator, so 38/45. Okay, three things. Without doing this whole problem, though, the answer is, we didn't do a negative, did we? We might have to backtrack just a little bit, but let's at least talk about this one. And we can start -1, so just be careful if you're starting a -1. But take a look at this, 3x plus 1 squared dx. That is not 9x squared plus 1. You cannot bring that in. What do you have to do there? You must write it out twice and then FOIL. Okay? You must write that out twice and FOIL. I forgot to look. We'll do one. We'll have more time tomorrow. Tomorrow's lesson is similar, so we'll backtrack. We'll do a few more. Maybe we can even start with that one. There is a trig one on your homework. We won't get that. We'll do that one tomorrow as well. There's one thing. Okay, so we still have to cover. Tomorrow we'll cover. This was a good one because we have a -a. I just want to show one where there's a negative area, though we talked about it, right? Don't panic if you get a negative area. We'll review that tomorrow. And trig. Okay. And the other thing, does anyone know when we do the antiderivative, we forgot to do something? The plus c, but take a look. It's okay, don't panic. I actually didn't mess it up. Because if I do b and I put a plus c, and then I do minus plus c, what's going to happen to those c's every time? They're going to drop out, okay? So we're actually okay with not doing the plus c. I just thought I'd tell you on that, because I don't want you to have home and go, oh, what about the plus c? And that's part of it. Tomorrow, we're going to have to remember it. So remember, I always say I forget the plus c. Sometimes you can forget it. All right, so at least try. If you get to one where you just don't know, we'll pick it up tomorrow. It shouldn't really only be the trig one, though. Right? But we'll cover this, and then we'll do actually the easier ones tomorrow. We'll talk about why they're easy.